Welcome to the third lecture in the 7th week of our course analysis of a complex kind. Today we'll learn about a really powerful theorem, namely the residue theorem. Let's start with the motivation. Let me remind you about isolated singularities. Remember that if f has an isolated singularity at a point c0, that means f is analytic in some disk centered at c0 with the exception of c0. Then f is a Laurent series expansion in that punctured disk, and the Laurent series expansion looks like this. We have coefficients ak and powers z minus c0 to the k for k from negative infinity to infinity. And the series converges locally uniformly in this punctured disk, and it converges uniformly as soon as we stay away from the boundary of that disk. Now notice the following. What happens when we integrate f over a circle of radius rho centered at c0, where rho is a little bit less than r? So this red curve that I just drew is a compact set inside the punctured disk, and therefore the convergence of the series that represents f is uniform on that curve. That means when we're integrating f over this curve, we're really integrating the sum over the curve. Because the convergence is uniform, we can interchange the summation and the integration. That is typically not the case, but under uniform convergence, you're allowed to interchange. And therefore, we find ourselves with a sum on the outside and the integration on the inside. That makes it quite easy to evaluate the integral over f dz, because now all we have to do is find all these individual integrals that have nothing to do with f itself. We simply have to find out what is the integral over z minus c0 to the k over the circle of radius rho centered at c0. We distinguish two cases, namely the case where k is not equal to -1 and the case where k is equal to -1. If k is not equal to -1, then this function z minus c0 to the k actually has an antiderivative that is analytic in the entire complex plane with the exception of c0. And the antiderivative is 1 over k plus 1, z minus c0 to the k plus 1. Because when I differentiate this function on the right, the k plus 1 comes down, cancels out with 1 over k plus 1, then the exponent becomes a k, which is exactly what I wanted. The only time where that doesn't work is when k is equal to -1, because I have to divide it by 0 in that case. So we have an antiderivative, which means the integral, because we're integrating over a closed curve, amounts to being 0. When k is equal to -1, however, I don't have an antiderivative of that type, and therefore the integral needs to be evaluated in a different way. We can certainly use the Cauchy integral formula, which is complete overkill, but we can also calculate the integral directly. Let me remind you how to find such integrals. What we need is we need to parameterize the curve over which we want to integrate. We're integrating over a circle of radius rho centered at the point z0. One way to parameterize such a circle is with the parameterization gamma of t equals c0 plus rho e to the it. We'll need the derivative of this parameterization, and it is gamma prime of t equals rho I to the it. Now we simply plug that in. So instead of z, I write z0 plus rho e to the it, and subtract the z0, and now I need to multiply with the derivative of the parameterization. And notice that a lot of things cancel out. In the denominator, the z0 goes away, and I'm left with rho e to the it. And now even the rho e to the it cancels out, so all I'm left with is the integral from 0 to 2 pi of I dt, and that equals 2 pi I. So when k is equal to -1, the integral that I'm interested in equals 2 pi I. Now remember what we actually were trying to find. We're trying to find the integral over f of z dz, where f had an isolated singularity at z0. So f was analytic in the punctured disk, punctured at z0 of some radius r, with an isolated singularity at z0. And we had looked at this Laurent series expansion, and we were able to bring the summation to the outside and the integration to the inside. And we're now left with this integral, z minus z0 equals rho, over z minus z0 to the k dz. We saw that unless k is equal to -1, this integral is not even there. So this whole integral, we just realized, is equal to 0, as long as k is not equal to -1. And so there's only one term left in the sum, namely the term where k is equal to -1. When k is equal to -1, the integral equals 2 pi I. And the only thing that's then left is the coefficient here, namely the a minus 1 coefficient in that case. And so we end up with 2 pi I times a -1. In other words, if I integrate a function with an isolated singularity around that singularity, with a curve that's small enough to fit into the disk where the function is otherwise analytic, then I get 2 pi I times a minus 1, where a minus 1 is the coefficient of the 1 over z minus 0 term in the Laurent series expansion. So therefore, this a minus 1 gets very special attention, and that's why I've been having you calculate a minus 1 in so many examples in the previous in-video quizzes. This a minus 1 is so special that it even gets a name. If f has an isolated singularity at z0, with this Laurent series expansion right here, then the residue of f at z0 is exactly this a minus 1 term. So this a minus 1 term is called the residue of f at z0. Let's look at some examples. We already calculated the Laurent series expansion of the function 1 over z minus 1 times z minus 2. We know this function has isolated singularities at z equals 1 and z equals 2, and so there's lots of different ways to find annuli in which the function is indeed analytic, in which we can find the Laurent series expansion. If we are interested in the residue of this function at point 1, then we need to find the Laurent series expansion in a punctured disk centered at 1. So for example, this one right here. So that's the disk we used, and we found that in that disk, f has a Laurent series expansion, which is -1 over z minus 1 times the sum that you see right here. The sum has only positive powers of z minus 1. The only negative power of z minus 1 is right here, and since it's the power z minus 1 to the -1, we see the coefficient a -1 right up here. In other words, a minus 1 is equal to -1, which means the residue of f at 1 is -1. If on the other hand we wanted to find the residue of this function at the isolated singularity at 2, we need to find the Laurent series expansion in the punctured disk centered at 2. Again, we do a partial fraction decomposition. We find that the Laurent series is 1 over z minus 2 minus this sum right here, which contains only positive powers of z minus 2. And therefore, this term here represents the term for k equals -1, and therefore the 1 right here, that's my a -1 for this Laurent series. So the residue of this function f at the point 2 is 1. So again, here's the procedure. If you want to find the residue of a function in isolated singularity, what you need to do is you need to find the Laurent series expansion centered at that singular point, and then read off the a -1 term. Here's another example. The function f of z equals sine z over z to the 4th. We saw that this function has a pole at z equals 0, so it's an isolated singularity, and we found this Laurent series to be 1 over z cubed plus minus 1 over 3 factorial times 1 over z, and so forth. So here we have two terms with negative powers of z, but this term in particular is the k equals -1 term, and this is the coefficient a minus 1 right there, because it's the coefficient in front of the 1 over z term, and therefore the residue of f at 0 is minus 1 over 3 factorial, which is minus 1/6. Here's another example. The function cosine of 1 over z. We saw this function has an essential singularity at 0, so the Laurent series expansion has infinitely many terms with negative powers of z, but we notice these are all even powers of z. There is no 1 over z term. Therefore, the coefficient of the 1 over z term must be 0, and therefore the residue of this function at 0 is equal to 0. How about sine of 1 over z? That function also has an essential singularity at the origin, but the Laurent series expansion has all odd powers of z. And indeed, there is a 1 over z term in the Laurent series expansion, and therefore the residue of f at 0 is equal to 1. Now remember the function cosine of z minus 1 over z squared. We notice that that function has a removable singularity at the origin, because when you look at the Laurent series expansion, there's no negative powers of z left. Therefore, again, there's no 1 over z term, and the residue of f at 0 equals 0. And here's a final example. The function 1 over z squared plus 1. The denominator factors into z minus I times z plus I. And again, we can do a partial fraction decomposition. I'm going to do it the similar way that I showed you a few lectures ago. I'm going to write the numerator as z plus I minus z minus I. The z's cancel out with each other, and I minus minus I is 2i. So my numerator is now 2i instead of 1. But if I divide by 2i, the new 2i in the numerator cancels out with the denominator 2i. The reason I did this is so that I can cancel things out again. I can now pull the fraction apart at the negative sign, and I notice that when I look at the first fraction, the z plus I term cancels out, and I'm left with 1 over z minus I. And if I look at the second fraction, the z minus I terms cancel out, and I'm left with 1 over z plus I. 1 over 2i's in front of it, and so here's my partial fraction decomposition of the function f. This function has isolated singularities at z equals I and z equals negative I. We want to find the residue at each of those points. So near I need to write this function in terms of powers of z minus I. I already have 1 over 2i times 1 over z minus I. The rest represents something that is analytic near I. I don't even have to bother finding the exact representation. I know an analytic function has a Taylor series expansion, and so I can write this analytic function as a Taylor series, k from 0 to infinity, ak z minus I to the k. And together, these two must form the Laurent series by uniqueness of the Laurent series. Therefore, the term for k equals negative 1 is the one here up front, and a minus 1 is 1 over 2i, which equals minus 1 half I. Similarly, when I look at f near negative I, my goal is to write f as a Laurent series with powers of z plus I. I already have one such power of z plus I right here, together with this negative sign, of course, and the 1 over 2i in front of it, so that you can see right here. And the rest is an analytic function near negative I, which again will have a power series representation ak z plus I to the k, for k from 0 to infinity. Together, the series and the first term form the Laurent series expansion of 1 over z squared plus 1 near negative I, and therefore this must be my a negative 1 term for this particular Laurent series. Therefore, the residue of f at negative I is minus 1 over 2i, which is 1 half I. Here, finally, is the residue theorem, the powerful theorem that this lecture is all about. Suppose D is a simply connected domain, and suppose f is an analytic function in the simply connected domain, except for isolated singularities. So here's my domain D, and I denoted the isolated singularities with these little x's. Let C be a simply closed curve in D, and suppose C1 through Cn are those isolated singularities of f that lie inside of C. This curve should not pass through any of the singularities. So here's my curve C, and it surrounds these two isolated singularities that are denoted C1 and C2. Then the theorem says the integral of f over this curve C is equal to 2 pi I times the sum of the residues of f at the points k that are inside the curve C. In the particular example I drew here, we would be simply getting 2 pi I times the residue of f at C1 plus the residue of f at C2. We've seen something like this already. We notice that if we integrate a function with an isolated singularity around a circle centered at the isolated singularity and inside the region where the function is analytic, then what we get as the integral is actually exactly 2 pi I times the residue of a function at the isolated singularity. So the residue theorem is an extension of this fact that we just discovered. Here's an example. Let's again look at the function 1 over z squared plus 1, which is analytic in the entire complex plane with the exception of the isolated singularities at I and negative I. I drew a bunch of curves, C1, C2, C3, and C4 in here. Suppose we first integrate over the curve C1, which is the red curve. By the residue theorem, I need to find 2 pi I times the residue of the function at the point that's surrounded by the curve, which in this case is just the point I. It's the only point that's surrounded by the curve C1. And we already found that residue, it's minus 1 half I. So altogether, the 2's cancel out, the i's multiplied to negative 1 cancel out the other negative 1, so the residue is equal to pi. If I use the curve C2 instead, then this curve C2 surrounds the point negative I, and therefore I need to look at 2 pi I times the residue of f at negative I, which we also found is 1 half I, and I find the integral equals negative pi. Now if I integrate over the curve C3, I notice that curve surrounds two isolated singularities, namely I and negative I. So if I integrate around C3, I need to look at 2 pi I times the sum of those two residues. But the two residues are minus 1 half I and 1 half I, and they cancel each other out. So together I get that the integral over C3 f of c dz equals 0. Finally, let's look at this blue curve right here. It doesn't surround any singularities, and so the sum is empty, and therefore I get the integral over C4 is equal to 0. Here again is this very powerful theorem that we just learned about. In a simply connected domain in which f is analytic except for isolated singularities, with a simple closed curve around which we're integrating, we can find the integral over f over this curve as 2 pi I times the sum of the residues of those singularities that are surrounded by C. In order to be able to really take advantage of this very powerful theorem, we'll need some more strategies and techniques that will help us to calculate residues. So far, we've been calculating entire Laurent series in order to find the residue of a function at a singularity, but there are actually other ways to find residues, and that's what we'll learn about in the next lecture.